My name is James Sternfield. I wanted to talk about some work I'm currently doing. I've been using Mathematica for 20 years. Really got involved with it as I started working with Dow Chemical, and I've retired since then, but still use it on my own projects of my own interest. I really got into the delayed differential equations because of the COVID lockdown, and Robert Nachbar posted a notebook that talked about different epidemiological models, and in there, he briefly talked about delayed differential equations and sort of dismissed them for his stuff. But it seemed to me that they really had a natural place there, and started looking at some of the challenges for using them, and realized that there was some need to really look at other ways of using and solving DDEs. So basically, I'm going to go through this fairly quickly. Not going to say a whole lot about delayed differential equations, except for the idea is that we have equations where we're trying to find a function whose derivative is a function of itself, time in general, and then the function at some delayed time. And there's various ways this can be approached. The standard way kind of gives a history, and we're going to kind of talk about that. What it does is basically we say, oh, we need that delayed time, so we're going to plug in the history we have, build up a solution to this now ODE, and calculate the next step. So this is a case where we're looking at a population DDE with the delay in what the population was maybe 2 years ago, to look at what the change of population. So here, the population is sort of limited by 250 counts. And as that gets closer to 250, then basically we'll get to a point where there'll be no change. If we start with this equation, put in, say, some initial condition of 100 people population before the initial condition, then basically we're putting in a function that's defined for the range from 0 to 2, that initial time step of 100. And our delayed differential equation becomes then an ODE, which we can solve, and we get this equation for that ODE. We can then use that to solve for the next interval from 2 to 4, and continue to generate the whole solution to the differential equation. If we use different histories, we will get slightly different curves for this particular problem. Because there's a discontinuity between the history and the curve we're generating, we get these changes in the slopes in the derivatives. The dotted lines are the second derivatives. And depending, like the blue is a fixed history. But eventually, as we go further and further in steps, that smooths out. The sensitivity, though, can be pretty big for some DDE. So here we're showing cases where we have 3 different slopes to our history. We're basically assuming it's a straight line. and we get three very different curves, and actually in this case it's going to continue to grow and be much different. There are analytic solutions to some DDEs. These analytic solutions in particular work are found for all linear homogeneous type things. They involve something called the product log, which is a special function in Mathematica. It's also known as a Lambert W function, and that's usually the way it's referred to in the literature. And basically, this general equation has a variety of behaviors. There's real and imaginary branches that can give solutions, and this allows you something to play with to really look at those different solutions. Here we see three different solutions that all have initial condition of 1. The blue one is really smoother than the other ones, and I'd like to think of that as sort of a natural solution. And this is sort of the way the idea of developing natural solutions kind of came to me, really looking for solutions that are less variation than the general any history you want type of results might give you. And so what I've done is really done research on what it might be to have a natural analytic solution. And sort of this is based on the idea of like minimal surfaces. We're trying to minimize the energy under the effects of that delayed differential equation, doing that in a way so that the we would preferably have a metric space that would determine when we have the minimal curve. The problem is that these DDEs are really an infinite dimensional metric space because we have a continuum of histories we can define. There are challenges for trying to get this to compare to two different solutions. I'm doing work in that direction, but not yet anywhere near presenting anything there. So instead, I'm really looking at how well the Taylor series of these possible solutions converge. So we're looking at approximations to the solution and taking those approximations and trying to find the one that converges in some sense the fastest. I will introduce some terms. I particularly find that I needed a particular type of spline, and I'm just calling it Taylor spline. There may be other names in the literature, but I'm not aware of that. Key points where we're actually talking about some initial point, a point that's a lag time behind it, and a point that's a lead time ahead of it. And those are also lead points and link points, and we're using that to build up our natural solution. This natural solution in general doesn't need a history, but it can use as many initial conditions as you want to give it. The main thing though is a lot of times that initial history may just be the trivial zero solution, especially for like linear equations. So we want to construct these natural solutions, and basically what we do currently, it would be an iterative process where we would guess at what the lag, link, and initial points, the key points are. Here I actually am using a quadratic fit to satisfy the DDE and get these positions. It seems to work well, but I've not proven whether that gets me to the ideal natural solution. So I'm working on that, but the idea is I could then just do iterations to modify this towards the natural solution. That would be much easier with a metric defined. In any case, at each of these points, we can define from that position the derivative at the initial point. From the derivative at the initial point, we can get the first and second derivatives at the lead point. And that gives us a good initial approximation to our natural solution. We then really look at that. If I take this approximate lag curve and integrate it over the DE as my history, I get a solution that's off quite a bit in this case, but it's also off in terms of it's not reaching the position of the lag point. I'm sorry, the lead point. And that's critical because if we're solving the DDE, we need to be able to have things integrate to where the lead point's at. We can add a higher derivative to this lag point and smooth this curve out, and we actually get a very nice fit. This is the new lag curve, and it comes very close to the original thing, but now we've taken this integral check, and it's now very much on top of the predicted curve. So that allows us to refine our initial approximation. We can then take those this derivative that we've added here, and with the DDE, increase the derivatives at these other points. To then further refine this, we introduce this concept of Taylor splines. And the idea is we have some sort of Taylor series at the lag point. From the DDE, we actually get a series at the initial point that's one higher derivative than the lag, and similarly two higher derivatives when we get to the lead. And we can use this concept of having a smooth curve to the degree of the lower derivative side that goes through the chosen nodes. And so this Taylor series spline does that, and is really one of the things that helps me to get towards a better shape of the curve. I'm going to skip back calculations. That's another way we can refine our solution or approximation, but it has challenges because there's not always a single solution to the back calculation where we take the information of the derivative and the current value at a point and back calculate from the implicit function the value of the delay point. So basically, that's the concept, but I'm not utilizing it in the rest of this presentation. So as I say, basically, we have now values that we've refined to some extent at these key points. We can use the Taylor series to define new points on the curves that we can start to fit and get improvements to solving the DDE. And so these blue points are now the new points we're looking at. I can take those new points and from the DDE calculate what the shape should be near these points. So from this lag point, I've calculated a Taylor series from the DDE at this new point. It's off from the curve we're forming. I guess I'm showing the actual principal solution, analytic solution behind there. We need to make adjustments so that this step and the Taylor series become, and the DDE solution become congruent, and that will allow us to get the curve smoothed out. Here, when we get to a higher derivative, we get a pretty good match at this lead point. So there's less need to do correction there. Because there's not a lot of time, basically my notebook has some examples for applying this on population DDEs. And so we go through some of the steps I've talked about specifically for that. This shows how well the refinements go for these solutions as we get towards a better natural solution. And that brings us then to looking at the SIR module, the SIR model for epidemiology. What this model does is basically create compartments for different parts of the population. So if we're looking at disease and how it spreads, we want to know how many people are there currently susceptible to the disease, and that's the S. I is the infectious part of the population, those who are infected. R is those who have recovered, and there's various equations can be used for sort of the force of the infection rate. And beta is the rate of infection. If we want to put a time delay, this is sort of one place where it can be put. There's various ways to implement that, but here the time delay is basically impacting the rate that we are recovering. So there's a delay in the recovery rate in this model. And that part of the population doesn't recover until they reach this time, and then there's only a rate that recovery occurs. And what happens, I took a model that was in Nashbar's notebook and refitted it to this equation using some initial points. This dotted lines are his solutions for this equation. When I put this time delay, you get a different behavior. So in his solution, basically everybody gets infected, and there's a final recovery because everybody's been infected. With my model, you find that there's actually some top level where most people have gotten infected, but nobody else gets infected after that point. And so time delays can have a significant impact on the model. And going to COVID-19 data in particular, I'm looking at the Wuhan data set, Hubei, China. This is actually in Wolfram's data depository, and pulled out some of the information here, calculated a few things from that information, but I've created a variable called removed, which is recovered plus the dead. The quarantine is basically how many cases that were detected are currently still active. And there are some issues with this data. These have to do with reporting stuff. They've changed the way they define COVID cases. They did some adjustments because it didn't agree with other provinces. And then they found a bunch more people dead. So those are like some of the significant changes in the data set. For this data set, I'm basically going to a model where the delay is actually, well, I've created a group now that is infective but not yet detected. And so there's a delay between when somebody initially gets infected and is infectious to when they actually are detected in quarantine. And so this model takes that into account. We won't actually fit the susceptible population because that'll be calculated after solving the DDE. And basically, we can take this and do, least square fit to part of the data set. And the model isn't quite good enough. This is the standard fit as we try to fit the two pieces of data that correspond to our model. We have this infectious undetected group that isn't available through measurements, but this gives an indication that, oh yeah, we can kind of get an estimate of how many people were infected at various times, which could be useful. If I fitted this data just to the quarantine detected group, I can get a much better fit. There's some issues with doing that, and really I need to add to this model. Part of the issue is the total population of who could be infected changes from the initial onset to as it spreads to larger area. So that's a big challenge. But basically we get some decent fit and some idea of the group of infected people. I provided some manual testing of this stuff here for those who want to check it out. So basically what I wanted to present here was just some work that's in progress. I'm still really finishing up some of the initial documents for publication. I believe that this has a lot of places it can be useful. I do not think that the Wuhan data that we were looking at as a whole in that particular model is the best place for natural solution, just because the sensitivity to the history is pretty minimal. But I do plan to look at it, or I have started looking at parts of that data and getting a better idea of how this natural solution helps there. And basically, I think that this will provide some ways to really use DDEs in places that they're sometimes very difficult to use. So I'm really looking for people to give input, and if they have problems that are interesting, to really let me know. I have here some of the advantages. I think I'll just open things up for questions at this point. Oh, and Robert, I see that you're here. Thank you. I greatly appreciate your presentation. It really got me going on this problem. So I'll open it up to any questions if there's anybody that has some. Otherwise, maybe I'll just take the moment to go through these slides that I skipped if there are no questions. I assume there's no questions in the Zoom session. So let me just say, this gives another way of looking at the work, but basically we take we look at quadratic capabilities for solving this thing. There's actually 5 solutions. 2 of them are trivial, 2 are problematic, and I've actually done work towards fitting these, but basically they allow for some interesting insights into finding natural solutions. But these are the 2 I'm focusing on. There's a question here about natural solutions. When do natural solutions most or least closely match numeric solutions to DDEs. Natural solutions are numeric solutions to DDEs. The problem with DDEs in general is that there's an arbitrary history that, depending, like if you do the most common thing, which is just to put in a flat history, it may be problematic for the behavior and not match your data at all. Like with the population data here, you might want to say, well, we had a low number below this, and even we had one person at this time. But the truth is, when you're making this stuff numeric, there is really more of a probabilistic quantification. So there's always a possibility that you really had a better time where there was a fraction of a person. And so initial conditions can be hard with flat things. With this, we can get where the data is actually good and get a solution that does not have a lot of variation. Any variation it ends up with is variation caused by the data we're trying to fit, or by the conditions we have forced onto the natural solution. So it will always be a solution to the DDE. I'm not sure. Okay, so the question is, have you come across good model support for the multiple waves besides hand waving about behavior modifications that seem partial and non-predicted? I'm not sure when we talk about multiple waves, if there's, in DDEs, you have a lot of multiple solutions. You get into unstable solutions, you get to bifurcations, and I assume that's really sort of where we're at, is that these bifurcations do exist, and they will show up even in a natural solution. But a lot of times you can find that they're not part of the natural solution, they're higher order solutions. And so it still supports these multiple ways, these multiple bifurcation. I'm hoping this is the sort of thing you're talking about, Paul, but in general, that's this way I'm interpreting your question. So you will find with even these DDEs, there are things that are very much like chaos type theory, variations, these very rapid transitions to unstable states. So I hope that's good. We're kind of coming to the end. I don't see any other questions. I appreciate your attention. I offer you to pull down the notebooks. If you have questions, please contact me. If you have interesting things to look at, I'd be more than happy to progress with that. Thank you again. And I think we will call it a wrap on this. Appreciate your attention. There will be papers. There are not papers yet. So the question was, are there any papers on natural solution? This is all my work, as far as I have some people working with me, but and I have some papers that are close to publication, but they've not even been submitted yet. So I may post one of these on like ResearchGate soon, but it's not available yet. Again, thank you for your attention, and much appreciation